Swayam Prabha. Digital India. Educated India.
Good morning, everybody. We have spent the last few lectures looking at the force method. Today, I am going to introduce another method. The force method actually lies under a broad class of what are known as compatibility methods, because if you looked at the equations were essentially based on getting a compatibility equation, and the number of compatibility equations are equal to the number of redundant forces that you generate. Today, we are going to be starting looking at a completely different approach. This is broadly classified as displacement methods. Just like we have force method, we broadly classify it under displacement method. And initially what I am going to be doing is I am going to look at what is known as the classical slope deflection equations, look at beams, and then quickly I will move on to more complex application of the same sort of methods. And we will see that just as we have used the principle of virtual force in the force method, we will be using somewhere along the line, we will be using the principle of virtual displacement to write down the displacement equations. Okay. So, let me just quickly move on to how to use the displacement method, and today I am going to concentrate essentially on what is known as the slope deflection equations and how to use the slope deflection equations to solve a statically indeterminate structure. So, let us look at what the slope deflection equations are. The slope deflection equations are given Remember, we had said when we had started looking at kinematic indeterminacy or the degrees of freedom, that a kinematically determinate structure is one such as the one that I have over here. In this case, if we look at it, the number of degrees of freedom that you can release, okay, if you look at the release degrees of freedom, we can look at it this way. We can say this rotation we can release. So, I will call this A, B. So, I will call this theta A, B. In other words, it is the rotation at A in the member AB. There is the rotation BA, And then there is also the delta BA, which is the lateral displacement of B relative to A. Please remember that. It is relative to A, that is delta BA. Okay. And another point that you will slightly notice if you look at books, this in standard slope deflection equation books, this theta is defined in this manner. I define it, what I define is, I always define rotation, anticlockwise rotation, as my proper orientation. I'll always have anticlockwise rotation as positive in my notation system. Then the slope deflection equations, and note that because I've drawn it in this way, the slope deflection equations become this. I'm just writing down the slope deflection equation, and then we will see how to, if I call this as L, and the flexural rigidity at EI, it's given as 4EI by L theta BA plus 2EI by L theta BA minus 6EI upon L squared delta BA, and MBA is equal to 2EI by L theta AB plus 4EI by L theta BA minus 6EI upon L squared delta BA. These are my slope deflection equations. These are the slopes, this is the deflection, and it essentially, these equations relate the moment at the two ends of the beam in terms, they give it in these terms. Okay. Now, these are the slope deflection equations, and normally this is where you start off. However, what I am going to do is, this goes along with my basis of never writing down an equation without knowing where it comes from. Okay. So, we are going to develop these equations of motion, okay, so that we know how they are developed, such that if there are any different kind of situations that we come up with, we can always obtain the slope deflection equations for those kinds of situations. Okay. So, let us see these slope deflection equations. Please look at the slope deflection equations. MAB is equal to 4EI upon L theta AB plus 2EI upon L theta BA minus 6EI upon L square delta BA. MBA is equal to 2EI upon L theta AB plus 4EI upon L theta BA minus 6EI upon L square delta BA. Okay. These are the classical slope deflection equations. Now, let us see how we can develop this. For this, let me go back to my old friend, the simply supported beam. Okay. In the simply supported beam, I am going to apply. You see, in a simply supported beam, I can apply any kind of loads. I am going to apply some specific loads here. What I am going to do is, I am going to apply a moment M1 at this point, and I am going to apply a moment M2. This is my loading on this beam. This is the only loading on this beam. And my brief is that under this loading, I need to find out this is A, B. So, I need to find out theta A B and theta B A. So, under these application, I need to, under this application, this beam will deform. Okay? And I want to find out what these rotations are under these loads. So, this is my question here. Okay. So, now how am I going to find this out? Okay, I am given the fact that the length here is L, and since only flexural deformations are considered, the flexural rigidity is given by EI. Okay, so my brief is given M1, M2, find theta AB and theta BA. Okay. Now, what I can do is, again, remember that since I am given M1 and M2, I can consider this structure to be first subjected to M1 plus M2. You see, principle of superposition. If this is my loading, I can say that this loading is equal to M1 equal to M1, M2 equal to 0 plus M1 is equal to 0 and M2 equal to M2. Right? I can always say this. So, and what would be the theta AB due to these two applications? I can find out theta AB and theta BA due to this, and I can find out theta AB and theta BA due to this, and if I add the theta ABs, then I will get these theta ABs. Okay? So therefore, the question here is very, very simple. I want to find out how much, and note that theta AB also I define as anticlockwise as positive, and theta BA, similarly here theta AB, theta BA, and once I find out in each case, I add the two up, I get these theta ABs that I am interested in. So let me solve first this problem, then I will solve this problem. Okay. Now under this load, what would be, how would I find out the rotations here? Well, first and foremost, find out, this is a standard displacement problem which we've already solved earlier. Okay, so I'm going to use the principle of virtual force to solve this problem. So first, I'm going to apply the real load, and then when I apply the real load, I get, this is my bending moment, M1 here, 0 here, linear, and this is the bending moment. I'm going to leave it up to you how to get this. Okay. Next, I want to find out the rotation at this point. What do? I apply a unit virtual load. Okay. If I apply a unit virtual load, what do I get? I'll get again a linear 1. And if I want to find out this rotation, what do? I apply a moment here corresponding to the rotation and draw the bending moment diagram. The bending moment diagram will be okay. So these are the bending moment diagram, and then all I need to do is to calculate theta B, I need to do theta 1 into theta AB, that's my external virtual work, is equal to, this is going to be my M1, this is going to be my M2, this is going to be equal to M1 upon EI dx, which is equal to M1 upon EI into, this is length L, so it's L by 2, this is the area under this curve, and the value at this at the centroid of this axis, which is equal to 2/3, and so this is equal to M1 L upon 3 EI. And similarly, theta BA is equal to M2 M1 upon EI dx. That is equal to M1 upon EI into L by 2. That's again the area under this curve. And multiplied by the, at the centroid, what is the value here? See, since the centroid is 2/3 or 1/3 from this distance, it's going to be equal to 1/3. And note that it is opposite sign, because if this is hogging, this is sagging. So this is going to be minus 1 upon 3. So this is going to be equal to M1L upon 6 EI. Okay, so because of this load, the theta AB anticlockwise and anticlockwise theta BA are going to be equal to this. What does theta B positive mean? It means that if you look at the, and theta BA negative, it implies that it actually is something like this, because theta AB is positive, but theta BA is negative, which means it's clockwise rotation, and clockwise rotation is negative. So this is how it looks, and under this loading, you would expect it to behave in this manner. Okay, so these are the values. Okay, now let's look at what if I apply M2. So I'm going to apply M2. So apply M2, and I need to find out how much theta AB is, that's positive anticlockwise, and how much theta BA is, which is positive anticlockwise. So under this loading, what would be the bending moment diagram? Again, I am not going to be spending time telling you how to do it. You should be able to do it by now, and this is going to be this sense. Okay, that's my M2, and then to find out theta AB, I need to apply moment here, and this is going to be equal to 1 this way, and virtual force here to find out this rotation, this is going to be equal to 1 going this way. So again, taking principle of virtual force, external work done to find out theta AB is 1 into theta AB. So 1 into theta AB is equal to, so this is M2 and this is M1, this is M2, this is going to be M1 M2 upon EI dx, and that is equal to M1 M2 upon EI. So this is going to be area under this curve, area under this curve, M2 upon EI, multiplied by area under this curve is L upon 2, multiplied by the value at this centroid. The centroid is 1/3 from this. So if you take 1/3 from here, you will get 1/3, and look at the opposite sign. So it will be minus 1 upon 3. So this is going to be equal to M2 L upon 6 EI. Similarly, if I do 1 into theta BA, you will see that area under this curve, which is M2 upon EI into L over 2, multiplied by the value at this point. If you look at the value at 1/3 from this point, this is 2/3, and look at them, both of them are the same. So 2/3. So this is going to be equal to M2 L upon 3 EI. So if you look at this, what does this mean? Well, theta BA is positive, that means it's this way, and theta AB is negative, that means it goes in this fashion. And indeed, under this load, you would expect it to move in this fashion. So these are consistent. So now, since I have obtained it for each individually, I'm just going to add both of them up. And when I add both of them up, what you get is theta AB is equal to M1 L upon 3 EI minus M2 L upon 6 EI. Theta BA is equal to M1 minus M1 upon 6 EI plus M2L upon 3 EI. Okay, so I've got the theta AB due to M1 and application of M1 and M2 together. Okay, so let us look at this. So now these are the rotations due to these moments. Now that means these rotations are related to the moments through these two equations. Okay, so I can rewrite this. Please look at this. I can rewrite this in this fashion. I can consider this as a vector which is equal to, let's look at it, L upon 3 EI minus L upon 6 EI minus L upon 6 EI, L upon 3 EI multiplied by M1 and M2. Okay, this, all I have done is I have written this in terms of a kind of a matrix equation. If you look at this, this implies theta AB is equal to this into this plus this into this, which is what you get here, and this is equal to this into this plus this into this, which is this. Okay. So, in other words, what you have is, given M1 and M2, which are external loads, okay, you are able to get theta AB and theta BA. Okay. Now you have to understand that I have taken actually loads M1 and M2. Now I can also say that, look, those are actually what is the bending moment at A in AB due to M1. You will see that the bending moment at AB due to M1 is M1. And what is the bending moment at B? It's going to be same as M2. Okay, I mean, this is fact, because if you look at it, you can actually go through it and do it yourself. In other words, what I am saying is that I can also replace M1 and M2 by MAB and MBA. Okay, and that's what I'm going to do. I'm going to say that M1 is equal to MAB and M2 is equal to MBA. If I do that, that means theta AB and theta BA are related to MAB and MBA through this. Now I can do the flip side. I can then write down MAB and MBA in terms of theta AB and theta BA, and that's what I'm going to do. How would that be? If theta AB and theta BA are equal to, I'm going to now take L upon 6 EI outside, so that, okay, this becomes 2 minus 1 minus 1 2 into MAB MBA. This is equally valid, because this is what I have got from the previous case. Okay, so now instead of writing theta AB and theta BA in terms of MAB and MBA, I am going to write down MAB and MBA in terms of theta AB. So what do I need to do? Look at this. If I pre-multiply this by the inverse of this, what would I get? I would get this, the inverse of this multiplied by theta AB is equal to the inverse of this into this, which is going to be what? A unit matrix into this. What would be a unit matrix? It would be the same. So that means this implies that MAB MBA is equal to this inverse into theta AB, theta BA. Now, what is the inverse of this? Well, it's simple. How do you find out the inverse? You find out the factors, and then if you look at this, the inverse of this, L upon 6 EI 2 minus 1 minus 1 2, the inverse. Please go back and look at your thing, will become 6 EI upon L. That is just this flipped. Inverse is obviously just this upon this. A scalar, what is the inverse of a scalar? 1 upon the scalar. So 1 upon this is equal to 6 EI upon L. And then the inverse of a matrix is, you have to find out the determinant. It's 1 upon determinant. So determinant is 2 into 2, 4, minus 1 minus 1 into 1, which is 1. So this is 3. So it is equal to 1 upon 3 multiplied by the cofactor of this is this. So this. The cofactor of this is minus of this. So that's that. The cofactor of this is the minus of this. So that's that. And the cofactor of this is this. So that's this. So if you look at it, this becomes equal to 2 EI upon L 2 1 1 2. So then if I rewrite, plug this into here, what I get is MAB MBA is equal to 2 EI upon L 2 1 1 2 into theta AB theta BA. So if I write this in a proper format, it will become MAB is equal to 4 EI upon L theta AB plus 2 EI upon L theta BA, and MBA is equal to 2 EI upon L theta B plus 4 EI upon L theta BA. Simple. Look back to the Stokes deflection equation. If you look back to the Stokes deflection equation, what did I write down? 4 EI upon L theta AB plus 2 EI by L. Now forget this term for now. These two terms I've just developed. Okay? That's this term has not been developed because I did not consider this delta. I just only considered theta AB and theta BA to occur due to M1 and M2. Okay? Now how do I include this? Simple. Let me just bear with me and I will take you through this. So these two terms, this relationship has already been developed here. Okay? And now we are going to develop the deflection part. We've already computed the slope part, and now we are going to be computing the displacement part. Okay? How do we compute the displacement part? Well, let's just bear with me. Take this. Take this situation. Suppose, now this is a pin here and a pin here. Suppose I were to remove this and let this go up by delta. Note that this delta is small compared to the L, so it is essentially small displacements. So how would this displace? Note that this is free to rotate, this is free to rotate. So if you look at the displacement pattern, I was going to use another pen. The displacement pattern for a simply supported beam would just be this. It will be a straight line, right? It will be a straight line, okay, where this angle would be delta upon L. Okay. So now let us look at the system that we were looking at, the original equation. How will I get a displacement here? I will just have to release this just like I released that and displace this by L. How will but note that the fixed end remains. So how will this displacement look like? This displacement will look like note that here, because they were simply supported and hinged, when I moved it by delta, I got displacement pattern which was exactly like this, and here because they are both fixed, the displacement pattern, the rotation has to be 0 here and the rotation has to be 0 here, and this is the displacement. So you see this and and this do not look like each other at all. Can I make this behave like this? Sure. Think about it. Remember that when I had this under an application of MAB and MBA, what happened? It went like this, where I got theta BA and theta AB, and I know the relationship between theta AB and SI. So let me take this situation. What I am going to do is, you see this is small displacement, so it doesn't really matter. I am going to now apply on this a moment MAB and moment MBA. I'm going to apply these two moments. Of course, I am applying them here. I am just showing it over here because I have displaced it. Remember that these displacements are always very small. I just exaggerate them to show them clearly. So if I apply moments here, what would happen? Think about it. Could I apply a moment MAB and MBA? Under MAB this happens. So can I apply a moment MAB such that the displacement pattern about this? Remember that this is also length L because this is small. Okay, this is length L. This happens. In other words, I apply a moment MAB and MBA on the simply supported beam to ensure that this displacement pattern essentially displaces in this way so that it mimics this displacement pattern. So that means, what are my rotations? Let's look at my rotations. What is my rotation? This is the undisplaced shape. Note, displacement is this way. This is my theta AB, okay, and this is my theta BA. Now, what are my theta AB and theta BA? Let's look at this. What is this angle? Delta by L. Now, is this clockwise or anti-clockwise? From to the tangent. From the undisplaced to the tangent. That is equal to, so if you look at this, theta AB is going to be equal to minus delta L. Why minus delta L? Because look at it, delta upon L is the magnitude of this rotation, that's for sure, okay, delta by L, okay, and the fact that it is clockwise makes it minus delta L. Similarly, theta BA is equal to what? Let's see, from to here, this is clockwise. So theta BA is also minus delta L. So that means what I am saying is, can I find out an MAB and MBA which would give rise to these? Sure I can, because I have already developed this. I can find out MAB and MBA given theta AB and theta BA just by applying this equation which I have developed. So I am going to use that. Let me use that. What happens? MAB is equal to 4 EI by L theta BA plus 2 EI by L theta BA. Okay, so if I put that in, and similarly BA is equal to 4 EI upon L theta BA plus 2 EI upon L theta AB, that we have already got there. So just substitute the values of theta AB and theta BA in here, you will see that MAB is equal to 4 EI upon L into minus delta by L. Note that theta AB is minus delta by L plus 2 EI upon L. Theta BA is also minus delta upon L. So plug that in. Excuse me. Plug that in, and what do you get? You will see that this will become minus 4 EI upon L squared delta minus and minus 2 upon L, and this becomes minus 6 EI upon L squared delta. Okay. And by definition, what is the delta? I have defined this as delta BA. So this is going to be delta BA. Okay. So I've got MAB in terms, and similarly you can get MBA, you will get it equal to this. So that means if I substitute all these factors, which is a theta AB, a theta BA, and a delta, if we put all those factors in, okay, if I have theta AB, theta BA, as well as delta, then what would be my MAB? I just add all of them up, and when I add all of them up, what do I get? MAB is equal to 4EI upon L theta AB plus 2EI upon L theta BA minus 6EI upon L squared delta BA. MBA is equal to 2EI upon L theta AB plus 4EI upon L theta BA minus 6EI upon L squared delta BA. Okay. We have just developed the Stokes deflection equations from first principles. Okay. So this is what I wanted to do. You have to understand where they come from, and then once you know those, you can actually develop these equations for any kind of member. Okay. You just have to see, here we considered that EI was a constant over the entire member. It is not necessary that all the time the member has to be uniform. You could have a non-uniform member also. But then all you have to do is, how did we evaluate this? We first found out, we applied loads M1 and M2 and found out theta AB and theta BA. Okay. Once we found those out, then we knew that M1 and M2 are equal to the bending moments at that point, which is MAB and MBA. And once we did that, we took the inverse. We got theta AB and theta BA in terms of MAB and MBA. Then we inversed it and we got MAB and MBA in terms of theta AB and theta BA. And that is, in a sense, is your Stokes deflection equations. And then we got the deflection part just by being innovative and seeing how to relate delta BA in terms of a spurious theta AB and theta BA. Okay? So this is the Stokes deflection equation. What can we do with the Stokes deflection equations? Let us look at a simple structure that we have. Okay? Let me take a very, very simple structure. Okay? I am going to take a very simple structure, and then I am going to say that, look, I am going to apply a moment here. Okay, let's just, I am going to take very, very simple structure just to illustrate how to use the Stokes deflection equations. So I have A, I have B, I have C. And this is, there is only one moment, only one load, and that is the moment. How did this moment come? Maybe it is because of some applied load over here. I am not bothered about that. This is the condition that. And is this a statically indeterminate structure? Of course it is. You know, I mean, there is no way. How many? What is the static indeterminacy of this? You have 1, 2, 3, 4. Okay, you will see that the static indeterminacy is 4 here. Okay. But in this application of Stokes deflection equation, you do not worry about what is the static indeterminacy. All I found out the static indeterminacy was just to illustrate to you that this is a statically indeterminate beam, and there is no way for a static indeterminate beam that you can find out the bending moment diagram. And my point here is, find bending moment Now, how do I apply the slope deflection equations to get the bending moment diagram? Instead of finding out the static indeterminacy, what you have to find out is the kinematic indeterminacy of this structure. Kinematic indeterminacy. Remember how we developed that? Kinematic indeterminacy, or I also called it as degree of freedom, degrees of freedom. How do I find that out? Let's go through this. How many joints? A, B, C, 3. So 3 into the 3 degrees of freedom per joint. Then we have to subtract the restraints. How many restraints? 3 here. The translation here, the translation here, and the rotation here, they are 0. So this is also restraint, 3 plus 3, and there's 1 degree. So that's 7. 7. Okay. Plus I have one constraint. What is that constraint? That the axial force in this member is 0. So that is 1. So how many degrees of freedom? 1. 9 minus 7 minus 1. And what is the degree of freedom? You will see that the degree of freedom is essentially this rotation. So what I want to say is that the whole point in this exercise is to find out theta 1. See, this is unknown displacement. So all I need to do is find out theta 1, and hopefully if I find out theta 1, then I should be able to find out the bending moments given theta 1. Okay? And that is the reason why, because we are trying to find out rotations and displacements, this method classically is called as the displacement method of analysis. Okay? So let's see how this step. Kinematic indeterminacy. So think about it. In the force method, what did you do? You found out the static indeterminacy. Once you found out the static indeterminacy, you then obtained the you identified redundant forces, and then once you found out redundant forces, you actually wrote down compatibility equations corresponding to the redundant forces, and that's how you solved it. In this particular case, it's just the opposite. In the force method, actually the redundant forces, you see, the only thing about the redundant forces is that when you put redundant forces equal to 0, you need to have a stable, statically determinate structure. That's all that is there. So therefore, there is uncertainty about which redundant force. In other words, there are so many redundant force systems that can create a stable, statically determinate structure that you and I may not identify the same redundant forces ever and still solve this problem correctly. Okay? Whereas, if you look at the displacement method, degrees of freedom, once you have the degree of freedom, can any one of you tell me that this is kinematic indeterminacy or degree of freedom is 1? Can you identify a degree of freedom which is different from this rotation? No. This is restrained completely, this is restrained completely. This is not allowed to go this way because of axial rigidity. So therefore, this is not allowed to go this way. So the only thing that can happen is this. In other words, in the displacement method, the degree of freedom identification is unique. You and I and everyone else would choose the same degree of freedom. There is no other degree of freedom to choose in this particular case. Okay? So there is a slight amount of uniqueness. In other words, once you identify the degree of freedom, you or I or anybody else cannot choose any degree of freedom. It has to be a unique degree of freedom. This, you will see later, makes this method, the displacement method, particularly amenable to use in computers, because you see, the computer is not going to be confused. In the redundant force, in the force application of force method, how is the computer going to determine the redundant forces? You have to identify it for it. But degrees of freedom, the computer knows which degree of freedom. Given a structure, it can always identify the degrees of freedom very, very easily. Okay? So this is the beauty of this, that the computer can actually, you can develop an algorithmic way which can be implemented on a computer using the displacement method. And this is the reason why the displacement method is the more popular method for analyzing structures in general. So therefore, let us now look at how to solve this problem. So this is my problem. This is my degree of freedom, and I have to find out this degree of freedom given this moment, and hopefully if I find out the degree of freedom, then I can get the bending moment diagram. Ultimately, never forget that the overall factor here is to find out the bending moment diagram here. So what are the steps? The first step, give theta 1 equal to 1. What will happen? Think about it. Theta 1 equal to 1. Theta 1 equal to 1 implies that this, at this point, the joint rotates by 1. If it rotates by 1, since this it cannot rotate, it's going to take up something like this. This is the displacement pattern that this structure. So this is the displacement pattern under theta 1 equal to 1. Note that when I say theta 1 equal to 1, understand that it is not 1 radian that I am saying. All I am saying is that theta 1 equal to 1 is, it's a very small, you can take 1 into 10 to the power of 4, who cares? The whole point is that it's unit rotation, however the rotation still remains small. All displacements that we are going to consider in this case are going to be small. Okay? So this is my rotation pattern. Now what next? What next is, I take this to a member level. I take member A, B, and I take a member B, C. Okay? Now, under this rotation, what does this thing look like? This thing looks like this. And BC looks like. So note, I have a situation where in a member, I know the rotations at the two ends and the displacement, if any, of B relative to A. Since I know these, can I find out the bending moments at the two ends, which are M AB, M BA here, and here it's going to be M CB, and this is going to be M BC. Can I find these out in terms of these rotations? Sure. Apply the slope deflection equations. What do they give me? Well, since theta AB is equal to 0, note, theta AB is equal to 0, theta BA is equal to 1, and delta BA is equal to 0. So I just need to plug that into the slope deflection equations, and my MAB turns out to be equal to, MAB is equal to 4 EI upon L theta AB, which is 0, plus 2 EI upon L theta BA, which is 1, minus 6 EI upon L squared into 0. This is equal to 2 EI upon L. Similarly, substituting, you get MBA is equal to 4 EI upon L. Or I can put this in this term, that this is given, these are the moments given theta 1 is equal to 1. If theta 1 was actually theta 1, which is an unknown, okay, then what would MAB and MBA? Just multiply by theta 1, right? This is linearity. So we can just find out MAB in terms of. Similarly, for BC, if I apply it, you will see that MBC, I'm not going to go into the details, you can apply it yourself, you will get it equal to 4EI by L, and MCB is equal to 2EI by L. I've got the member end moments. Now, once I've got the member end moments, what do I do? Well, let's look at it. Let me draw it. And I'm now drawing the original structure. The original structure is this way. And what do I have? I know MAB, I know MBA, I know MBC, I know MCB. I've got these in terms of theta 1. Okay. Now, by equilibrium, let's look at a few things. By equilibrium, what is the moment at this point? The moment at this point is in this fashion, that is equal to MAB, and the moment at this point is equal to MBC. And remember that at this point I had applied a moment M1. So if I take moment equilibrium of this, I'm only taking moment equilibrium of this. What do I get? I get MAB plus MBC minus M1 is equal to 0. So therefore, MBA plus MBC is equal to M1. This is my equilibrium equation. Okay. So now what is MBA equal to? If you look back at it, MBA is equal to 4EI upon L theta 1. And what is MBC equal to? Also 4EI upon L theta 1 is equal to M1. So that means 8EI upon L theta 1 is equal to M1, which implies theta 1 is equal to M1 L upon 8 EI. I have found out my unknown rotation, and once I have found out my unknown rotation, then now once I know my unknown rotation, can I find out my MAB, MBA and MBC? Of course, I've got them all in terms of, so now since I've got theta 1, my MAB is equal to 2 EI upon L into theta 1, and theta 1 is M1 L upon 8 EI. So which, if you look at it, will become M1 upon 4, MBA, which is 4 EI upon L theta 1, is going to be M1 upon 2, MBC similarly will be M1 upon 2, and MCB similarly will be M1 upon 4. So if I look at it, what is my, I have MAB, MBA, MBC, MCB. And since I know all of these, I can draw the bending moment diagram, because this is now a statically determinate structure where I know the member end moments. And if I were to show you the member end bending moment diagram, okay, this is M1 upon 4, this one is M1 upon 4, and if I were to draw the bending moment diagram, it would look like this. I'll leave that as an exercise for you, where this one, this is M1 upon 2, this is M1 upon 2, this is this way, and this is this way. Why is there an discontinuity at this point? Well, what is the discontinuity? M1. And what is the applied moment over here? M1. So this is the discontinuity. Okay, here I am just going to now quickly state that how did we go about applying the displacement method? We actually applied, we found out the kinematic indeterminacy, then found out the degree of freedom. Then next step is corresponding to the degree of freedom, give a unit displacement and find out the displaced shape of the structure. Once you find out the displaced shape of the structure, you can find out the displaced shape of each member. For each member, then once you know the displaced shape, you know the member end rotations and the displacement of one end relative to the other, and you can apply that into your bending moment, into your slope deflection equations to get the bending moments at the two ends. Once you get the bending moments at the two ends, you can then apply equilibrium equations to relate the unknowns and find out the value of theta 1 in this particular case. And once you know the value of the rotations, then you can always go back, substitute and get the member end moments exactly. And once you know the member end moments, then you have a statically determinate structure for which you can find out the bending moment diagram. These are the steps in what is known as the displacement method. Don't worry if you're not able to understand the quickness with which I have gone through. I have just established the procedure for you today. I have taken a very, very simple question and gone ahead with it. This I am going to expound on. Since I know that this is a topic that you have not covered earlier, I am introducing the topic to you today, and then later on you are going to see how this method is developed over the next many lectures. Thank you very much.